So if you don't have a question, so I could just give you very yeah.
Can you go over the mechanism for synthesizing the vicinal diodes?
Vicinal diode. Oh, that mechanism, we don't really talk about we didn't really talk about finds the possible details. Okay, but the vicinal diode synthesis covered in this chapter. Next chapter is another vicinal diode synthesis, different. Okay, but in this chapter, I assume you are talking about say the uh, this reaction, right? So the feature of this reaction is you will have important the stereochemistry, the two OH groups on adjacent carbon will be added to the CC double bond in a same manner, meaning the two OH groups added from the same side of the CC double bond. So the mechanism of this reaction, is the key component in this reaction is this one. And although this osmium tetraoxide is used in a catalytic amount, so usually say something let's say 0.1 molar equivalent of alkene. Okay? And the reason we don't want to use a lot because of this compound is a gas. It could be a gaseous compound, and also it's expensive and toxic. So the a number of reasons. Okay, but what is the key feature? If you look at this compound, what you expect is it has like the four oxygens bound to the central metal. So that central metal, obviously, you can expect, the central metal will be metal. Oxygen is very electronegative, so the central metal will be very electron hungry. So overall, this osmium tetraoxide is very hunger for electrons. Okay, so that make osmium tetraoxide powerful electrophile. Okay, so but its reaction with alkene is it's kind of interesting. It's basically if you have the say alkene here, let's say. So you have this cyclic form of electron transport. It happens in a constant manner. So this reaction can be compared with another reaction we have seen in organic 1, just to help you visualize how does the reaction work. If you recall the similar reaction in organic 1, okay, if you recall this, and then this one leaves. So that is the rate limiting step in the halogen reaction with alkene. So this one lead to the brominium ion, okay, and bromide. And because of the two bonds, the two carbon bromine bonds, okay, formed at the same time. So the CC bond here, sigma bond, does not have time to rotate. So that's why this addition, always syn addition. Same thing here, because these two carbon-oxygen bonds, they form at the same time. So this CC bond does not have time to rotate, okay? That's why these two carbon-oxygen bond always formed, from the same side of the CC double bond. That's why this addition is syn addition. So this lead to the intermediate OS So this is a syn addition. Let's assume a adder from the bottom of CC double bond. Okay. So let's say wedge. Okay. Both of them add to the bottom of CC double bond. Okay. So you get this one. Okay? And then then this additive will be oxidized by the organic peroxide, like this one. This is organic peroxide, and the peroxide usually they typically, because of the oxygen here has oxidation state, overall has -1, and we know oxygen usually wants to have a oxygen state of -2. Okay, so that's why peroxide usually are reasonable good quality of oxide. Okay, so this oxide oxidize this whole thing, okay, in the presence of OH minus. So it's the exact mechanism, it's basically the reaction happens on those bonds. Okay, the reaction happen on the mostly these two oxygen osmosis bonds. Okay, so it does not impact this CO bond, so that give you the OH and OH, and the one these two the osmium oxygen single bond is oxidized, you can regenerate the osmium tetroxide. So that's you can see that from this cycle you can see osmium tetroxide beginning start as a reactant, and it's regenerated at the end of the cycle. So obviously this osmium tetroxide can react with a second or more of alkene. So basically signifies the fact that this osmium tetroxide is a catalyst. Okay, and the goal of peroxide is oxidize this reduced form of after electrophilic addition, osmium tetroxide in this compound, osmium has oxidation state of +6 instead of here it's +8. Okay, so this is osmium compared to the osmium tetroxide is reduced, and the peroxide major goal is oxidize this guy back to the osmium the tetroxide. Okay, the hydroxide form, the OH minus here does the job of the cleave the osmium oxygen bond. Okay, so that is the relevant mechanism. The details, if we're not gonna need it, I'm not gonna talk about. If we're gonna need it, I'm gonna talk about. If we're not need it, not. So the key feature is the first recognize osmium tetroxide as electrophile. Then because it's two CO bonds formed at the same time, so these two CO bonds must add to the same side of the CC double bond. Therefore, the formed two OH group diol, okay, they must also add, effectively, they must add from the same side of CC double bond. So you will get the cis diol in general. Okay, if you have the double bond is part of ring. If double bond is not a part of ring, you will not see the impact easily. Because if double bond is not part of ring, then after addition, that single bond can freely rotate, so you won't see that effect easily. Okay. Does it answer your question? Okay, that's next. Yeah, right. Quiz reaction? Okay. Well, which reaction are you talking about? So let me see. Quizzes. Edit the test. Okay. You talking about this?
Yeah.
Well, so the key knowledge, key topics are being tested here is you know there are in this compound there are two double bonds, okay, and both double bonds potentially can be reduced potentially, okay. Potential depends on what kind of reducing agent you are using, okay. But here we are using sodium boron hydride. It's an ionic nucleophile. Okay. Because it's ionic nucleophile, it's the real nucleophile. You know if view it based on that ionic equation is BH4 minus, so it's N9. Okay, so because of the real effective nucleophile is N9, you will highly selectively attack what kind of functional groups? Yeah. Huh? Polar, yes. Polar functional group and attack the positive charged atom. So out of these two functional groups, the CC double bond is not polar. No, unless the two substituents, okay, they are, unless the two substituents connect to the double bonded carbon, they are substantially different electronic characters, okay? But the CC double bond itself is not polar, okay? But the CO double bond itself is inherently strongly polar and it plays a large amount of positive charge on the carbonyl carbon. So where you have these two double bonds in the same molecule, only the CO double bond, the polar double bond, will be reduced by an anionic reducing agent. So if, on the other hand, if the reducing agent is hydrogen gas, hydrogen gas is not polar, so it doesn't have much selectivity. Okay, so both can be reduced. So basically, if you knowing that, the double bond will be kept, okay? So basically, you are making choice of this or this, either this or this, okay? But the next knowledge point I want you guys to know to answer the question is when you have the metal hydride reducing agent reduce the carbonyl group, the hydrogen connect to the carbonyl carbon is from the metal hydride reducing agent, okay? Basically here, this guy, okay? And the hydrogen connect to O is from the proton donor. Here is just the alcohol, the OH proton from the alcohol or OH proton from the water, okay? And this one is H, this one also H. So you have two H's added across the CO double bond. So it has to be this one. Because you don't, if you see the CH3OD as a solvent, okay, if you saw that one, then this would be the correct answer. Okay. Yes, Julia.
So when you do this type of reaction, it doesn't do anything to the double bond. Because there was a question that it was like it went from if you scroll down here, it like reduced the whole thing from double bond.
Maybe it's earlier one.
Yeah,
Yeah. See, that's depend on what kind of reducing agent you use. So if we are using ionic, the reducing agent, and if the spectator ion is a cation, so the real active reducing agent is anion, then it will be very picky about what kind of functional group you would like to reduce. So generally want to reduce highly polar functional group. So that's why lithium aluminum hydride, sodium boron hydride, both of these two reducing agents will selectively reduce the polar one. Okay? But if the reducing agent is hydrogen, we know it's not polar. It doesn't have much selectivity. In real world, there's some slight selectivity, okay? But the selectivity is not clear cut, okay? Because after all, those two double bonds, they are different. So you might see some subtle reactivity difference, but it's really subtle.
So it's gonna do both.
Yeah, so you usually gonna do both.
And for the first one, the lithium you can use the water for the bromine using not, right? In the second step, like this first and second answer.
Yeah.
You can use water for the first one, and for the second one, it has to be executed the whole way, right?
What's the whole way? You mean?
Like the lithium aluminum hydride
Yeah.
and the sodium bromine hydride.
Yeah.
For the lithium, you can use water for the bromine using not, right?
Oh, not bromine, boron hydride.
Boron, I'm sorry.
Okay. Now you also can use water.
But also in the second step, though, right?
See, the biggest difference is this is actually experimentally convenient. Is a lithium aluminum hydride. You have to do two-step reaction as shown here. Okay. In sodium boron hydride, you can do one-step reaction, just using water. If water dissolves your reactant, okay, or alcohol. If water does not dissolve your reactant, I can't remember the solubility of this guy. I don't. It might be somewhat dissolvable in water, okay, but the alcohol certainly can dissolve it, okay. So this one actually you could use the sodium boron hydride. If this guy soluble in water, you could just dissolve this in water, then throw in sodium boron hydride. That reaction can complete. You don't need to do two steps. But the lithium aluminum hydride, you cannot do that because the water will immediately react with sodium boron hydride. I'm sorry, lithium aluminum hydride, okay? Because lithium aluminum hydride is the more reactive one. Its general behavior, just like a Grignard reagent or organolithium, can be easily deactivated by moisture or alcohol. But the sodium boron hydride is just reactive enough to react with ketone aldehyde carbonyl, but also will not react with water or alcohol at ordinary conditions. That's the biggest difference. So if your goal is reducing ketone or aldehyde, you almost certainly going to choose sodium boron hydride because it's you don't have to pay the extra cautions to make sure the reaction is extremely dry. Just ordinary condition, benchtop, you can do it. Okay, but if you need something, if you have something need to use lithium aluminum hydride, at least the reaction must be protected by nitrogen. Okay? You cannot do open bench reduction. It won't work. Open bench reduction will kill lithium aluminum hydride. Sodium boron hydride, you possibly can do open bench reduction. Just put in your reactant, dissolve the alcohol, water, dissolve it, then put the sodium boron hydride, stir it. That's it. Okay. You may not need the nitrogen protection even. But the lithium aluminum hydride, you have to, in the first step, you have to carefully avoid the water. so that lithium aluminum hydride will not be deactivated prematurely. Okay? That's biggest difference. And the lithium aluminum hydride is the only reagent you can reduce carboxylic acid. Only, okay? Not any other thing. Next question. Now, if I don't see next question, you can formulate your next question. But I want to give you the general, let's say compare and contrast the alcohols and the phenols. Okay, so if you look at the alcohols and the phenols, here I'm using a primary alcohol as example, but the general reactivity also applicable to secondary alcohols. Tertiary alcohols a bit different. Okay, we're going to talk about later. Okay, so the common feature of alcohol and the phenols is that they have OH group. Okay, so that's the reason why I put these two chapters together. Okay, so that's a common feature. So what property come with the OH group? Can anyone tell me what property you can expect come from OH group? Yeah, acidic. Okay, so the this proton is acidic. Okay, somewhat. Okay, so but difference is this pKa is usually around 16, and this pKa is usually around 10. Okay, so that's difference between acidity. Okay, so this acidity, even before we have a more detailed discussion in chapter 23, we can justify why the phenols are more acidic. Basically, you see, based on inductive effect alone, you can say phenol will be more acidic. Why? Because of we know the acidity of a proton is impacted by inductive effect of neighboring group if you have electron withdrawing group around. Okay, so if you compare these two OHs, the difference is the alcohol OH connect to the sp3 hybridized carbon. Okay, in phenols, the OH will connect to a sp2 hybridized carbon. So I hope you have, I hope that this has been formally established for you. The relative electron activity of carbons depends on its hybridization state. So the sp carbon is more electronegative than sp2 carbon, which is more electronegative than sp3 carbon. Okay, that's what we learned in organic 1. Okay, so because of in phenol, this carbon is sp2 hybridized, so immediately you can make argument. This more electron withdrawing than sp3 hybridized carbon can make argument why this hydrogen is more acidic, okay, than the alcohol. Okay? But that's acidity of OH is one property. But if aside from acidity, what are the other property come with the OH group? Luciano?
bonding?
Yeah, that's true.
Yeah,
That's true.
Yeah,
But hydrogen bonding, but when we consider reactivity, right? Hydrogen bonding usually is a secondary effect. Okay, it's a more important feature there. That dictate the reactivity you can associate with OH group. Yes, acidic is correct. The ability from hydrogen bonding also correct. Both are correct, but in organic reaction, I'm not saying ability from hydrogen bonding is not important. Just is less important than the property. I would like some of you can point out what is the most important reactivity you can associate with OH group. Yeah. Yes, itself is not a good living group. Again, that's correct answer, but not the answer I'm looking for. There's a even more important feature that associated with OH group. That's the core part of many reactions you will be seeing in chapter 16 and 23, the core part. Core reactivity you can associate with OH group.
The lone pair for
Huh?
the lone pairs for oxygen.
Yeah, it is dictated by the lone pairs, but those lone pairs give OH group what capacity? So if you think about, the potential energy of electron pair in a molecule, okay? So what kind of electron pairs are most unstable in a molecule? See, let's look at it. Let's say, I'll give you some examples, okay? Sigma bonding pair, okay? Pi bonding pair. And a lone pair. So, which of those pairs, three top pairs, which kind of pairs are most unstable or least stable? Sigma bonding pair, pi bonding pair, or lone pair? Lone pair. Why? Because sigma bonding pair, for sigma bonding pair or pi bonding pair, they are stabilized by two positively charged nuclei that involve that covalent bond, right? Two of them, okay? Just the stabilize a different way. One is just a sigma bonding pair. The pair is exactly, like at the center between the two nucleus. If these are two nuclei, the sigma bonding pair is in the middle, is here, okay? And the pi bonding pair will be above and below, okay? And the lone pairs only stay with one, the atom. So if we look at all kind of traditional electron pairs you might see in organic molecules, lone pair one is the least stable one, okay? Least stable one. Least stable means they are most reactive one, okay? So if you have available lone pair, it's that's the kind of electron pair most likely to be donated. Okay? So if once you have OH group there, the first thing you think about, other than acidity, hydrogen, these are all correct property associated with OH group, but the most important one is the OH group has that lone pair. That lone pair can be donated. Either make this OH group bearing compound and potential nucleophile, or the OH group can serve as the electron donating group to the rest of the molecule. Like here, in case of a regular alcohol, OH group makes the alcohol potentially serve as a nucleophile. That's the main reaction you will be seeing in chapter 16. The alcohol group will serve, the OH group of alcohol will be served as a nucleophile with oxygen atom as nucleophilic attacking atom. And then in case of phenol, okay, the story is a bit complicated, okay. So the oxygen lone pair still can serve as nucleophile, attack something else, but because of this carbon is sp2 hybridized, so the oxygen lone pair can also donate to the ring, okay. That makes the ring, has a higher electron density than normal aromatic ring. We learned this effect in chapter 13. And if you recall, in chapter 13, we consider OH group is a powerful, very powerful electron donating group and activating group. That's what we learned in chapter 13. That's the reason why it's, OH group is a powerful electron activating group and electron donating group. Okay, so that makes the reaction of the phenol is a bit more complicated than the alcohol. Why it's more complicated? Because now the phenol has phenol is considered as a bifunctional, the reactant, has two potential nucleophilic sites. One is the OH group with oxygen as a potential nucleophilic atom. The other one is the aromatic ring with those three ring carbon as a potential nucleophilic attacking atom. Okay, that is for phenol. But for alcohols, when alcohol serves as a nucleophile, only potential site is the oxygen atom, no other possibility, because this carbon is sp3 hybridized carbon, it cannot accept oxygen lone pair. Okay, it cannot. Okay, so the alcohols, if it serves the nucleophile, then the nucleophilic atom must be oxygen, no exceptions. Okay, always oxygen atom if alcohol serves the nucleophile. Okay, no other possibilities. Okay, but then if you look at this particular molecule, RCH2OH, so this one is a potential nucleophilic attacking atom. Okay, then this guy, we know this carbon, the carbon connect OH, we can call it alpha carbon. This alpha carbon, okay, or hydroxy carbon, it's heavily positive polarized. Okay? Heavily positive polarized. So if you have a nucleophile come in, you will attack what atom? If you have nucleophile. If you have nucleophile coming, you will attack this one. You will attack this one. Okay. But usually, alcohol cannot directly react with nucleophile. Why? Because if a nucleophile, comes in attacking, yes, you would love to attack this carbon, okay? But such attack will not be productive, because if this attack was successful, this OH minus would be a leaving group, right? And this leaving group, why it's not an impossible leaving group? Because of just think about it. If this guy does leave, okay, you have leave in the form of hydroxide ion, okay? Hydroxide ion basicity can be measured pKa of water, okay? It's around 15.6, around 16, okay? So it's not a good leaving group by any measurement, but not a totally impossible leaving group we consider called bad leaving group, okay? it's under certain conditions can serve as a feasible living group, but it's bad. Okay, bad. It's not impossible, but it's bad. Okay, so that's why it's just you throw in a standard nuclear file. Say you have throw this in, you won't react with alcohol. We are not, because the OH group is a better living group. Okay? Reaction won't happen. Okay? So under the obviously, if you have this one, just the other alcohol, this even worse nucleophile, because we know alcohol can be nucleophilic, but if you recall the nucleophilicity, I believe there's a table in chapter 6, organic 1. You know, there's a relative nucleophilicity of different nucleophiles. Neutral alcohol and the water, they are generally, the nucleophilicity is about 1, okay? And the conjugated base, about 10,000. So, you know, neutral alcohols are poor nucleophile. So if you think about another culprit of alcohol, if you think about, okay, the poor nucleophile, do you think can do this? Obviously won't, okay? It will not be happening, okay? However, if you mix, okay, if you mix the alcohol with non-nucleophilic acid, I hope you guys can remember a few non-nucleophilic acid, like sulfuric acid, phosphoric acid, you know, the chloric acid. These are a few examples of non-nucleophilic acid, okay? And also including a number of organic versions of the sulfuric acid. This one, sulfonic acid, can be considered as organified, you know, the sulfuric acid. So the advantage of sulfonic acid is that you know, it has better solubility in organic solvents. Okay, so we often can use sulfonic acid as a replacement for sulfuric acid. Okay, but you know, all those three acids, they are called non-nucleophilic acids. Okay, so if you put those non-nucleophilic acids into the alcohol in catalytic amount, so what will be happening is that we know those acids can protonate part of the alcohol. Okay, part of alcohol. Okay, so then in that solution, alcohol, non-nucleophilic as a mixture, we're going to have two kind of species. Obviously, this one's major. Before reaction happens, this one gonna minor. Let's say if you only add 0.1 molar equivalent of acid, okay? So the neutral alcohol will be the major one, the proton alcohol will be minor one, okay? So what's the difference between these two guys in terms of the reactivity? So now you see that in the protonated alcohol will be still, you see the neutral alcohol potentially can serve as a nucleophile with this one as a nucleophilic. Let's say, let me color code it, okay? So you see that nucleophile is blue, electrophile is red, or other way around? Which one you think? Which one you prefer? Nucleophile blue or electrophile is blue? Okay, nucleophile blue. Okay, I heard one opinion, so let's take a. So for the neutral alcohol can serve a dual role. Okay, this one is nucleophilic atom. This one is electrophilic atom. That's neutral alcohol. Okay, but for protonated alcohol, do you think this oxygen? Yes, still one lone pair available. Do you think this oxygen can serve as nucleophilic atom anymore? Although it has a lone pair, but now it's positive charged. So lost the ability to serve as a nucleophile. So only thing, so the proton alcohol only can serve as electrophile, okay, with the original OH carbon serve as an electrophilic atom. And the other difference, okay, is that because of now this oxygen is a positive charge, the full unit of positive charge. So if you look at the amount of positive charge on this carbon, say delta 1, this is called delta 1, okay? This is called delta 2. So which one going to have greater amount of positive charge? One. Why one is greater positive charge?
The oxygen the electrons themselves, so.
Yeah, but the bottom one, do you think the oxygen stop pulling electrons towards the cell after being, after you impose a positive charge on it? Do you think it stop pulling electrons or even pull more electrons?
No, it's not.
So see, the oxygen is electron hungry. Okay? If you impose a positive charge on it, make it even more electron hungry because you want to have more electrons. Now you impose a positive charge on it. So just like if someone, the wants more money, then now this person owes like additional $10,000 owes. Okay, do you think want more money? Of course, want more money because I have big hole in my wallet. I need more money to fill up my hole. Same thing here. So the bottom one when the positive charge imposed on the oxygen, so it will be more electron hungry. So that the positive charge, the delta 2 will be greater than delta 1. So that make delta 2, okay, will be greater than delta 1, okay. Exactly how much greater? I'm not going to give you exact answer because I didn't have a careful measurement on it, but probably at least 0.4, 0.5 units greater positive charge on it, okay. So that means that in the protonated alcohol, the carbon become more electrophilic. Okay? This is a property 1 of a protonated alcohol. Property 2, potentially even more important. If the neutral alcohol serves as a nucleophile, if the leaving group is what? Is OH minus, okay? Right? If for this one, okay, OH minus leaving group, but if the protonated alcohol serves the electrophile, this one is the leaving group. Water is a leaving group, okay? And again, if you can recall the organic 1, chapter 6, water is excellent leaving group, and the OH minus is a bad leaving group. It's still feasible under certain conditions you will see in the later part of the organic 2, but generally it's a bad leaving group. But water is excellent leaving group, okay? This is bad. It's feasible but bad, okay? And this one is excellent. So what does that mean is after protonation, the alcohol's ability to serve as electrophile is greatly enhanced, probably like 1,000 times, 10,000 times, okay? For two reasons. More electrophilicity as a original hydroxy carbon and the better leaving group, okay? So with that dramatic enhancement, then this took, you still have neutral alcohol in the system, okay? You have this excellent electrophile here, excellent electrophile with much more electrophilic carbon and a better leaving group. Yeah, these two guys react. Okay, so that is what what happens when you mix, when you add a non-nucleophilic acid, okay, into if you add non-nucleophilic acid into a primary alcohol, so that's what will be happening. Okay, so this one attacks here, okay, and this one leaves. So if you have this alcohol, you add, say, sulfuric acid, okay? So that is the rate limiting step. So if you look at this overall reaction, the driving force is not huge because when you are forming carbon-oxygen bond, you are breaking carbon-oxygen bond. So this reaction is kind of equilibrium reaction, okay? So, and they usually works best for primary alcohols because for secondary alcohol, attacking, see this kind of attack is what kind of attack? Do you think it's SN1 style of attack or SN2 style of attack? Just for this rate limiting step. Yes, SN2 style of, the attack. So if it's SN2 style attack, it depends on the nuclear steric hindrance at the electrophilic carbon. So yeah, it works best for primary alcohols. Okay. So secondary alcohol maybe okay. Tertiary alcohol doesn't work this way. Okay? This works best for primary alcohols. So that's and the many of alcohols react with this manner. Okay, and you also will see that those alcohols, okay, can react with chromic acid. Let's say CHOH react with chromic acid. And when it reacts with chromic acid, the same thing. The key reaction is still the hydroxy group serve as nucleophile, attack if the nucleophile attack the most electrophilic atom, here is a chromium atom. The chromium atom obviously carries great amount of positive charge. Okay, so detailed mechanism I will not really go through go through that much, but eventually will lead to the chromate ion. Okay, and then this once you form the chromate ion, and the next step is that's kind of a bit odd, but but you actually can understand using the similar reaction, similar mechanism we have seen in organic one. So once you form the chromate ester, okay, then water can take this proton away, okay, and then this one moves here. This kind of just like a beta elimination reaction, but instead of you have the beta elimination reaction, usually this one is a carbon, okay, but here we have oxygen here, but it works same way. So then this electrons go to the chromium. So this reaction is driven by the strong desire for chromium 6 to be reduced, because chromium 6 has a pretty strong oxidation power. So the pair of electrons goes to chromium can reduce it, become more stable. So this is driven by oxidation power of chromium. So this become let's say maybe this, okay, or you can come to here, okay, become this, okay, reduce the form of the chromium, okay. So then this supposedly, gonna reduce the, the aldehyde, oxidize the primary alcohol to aldehyde. But if you carry out this reaction in water, the primary aldehyde will immediately react with water. This reaction we're gonna learn in great detail in chapter 17 or 18, I forgot, just either 17 or 18, okay, become this this guy, okay, then this guy can further react with the chromic acid, okay, eventually lead to the carboxylic acid, and that reaction we're going to talk about in a later chapter. The key feature is if you have a primary alcohol, okay, if you have a primary alcohol, and if you treat with chromic acid in water, you will get the carboxylic acid. Basically, you will be oxidized twice, okay? You will be oxidized twice. So if you have primary alcohol, treated with chromium 6, and in water, okay, you will basically the alcohol will be oxidized twice, okay, become the carboxylic acid. The detailed mechanism we're gonna talk about in a later, later chapter, okay. So I think we can even probably we can talk about now. So basically, so the key part you see is the alcohol is nucleophile, so react with chromic acid, form this chromate ester, and that form the chromate ester. If chromate ester has at least one hydrogen on the carbon connect to the oxygen, you can undergo this beta elimination reaction. So this is a key reaction for the oxidation to proceed, okay? If you have, these two, the existence of those two CH bonds, okay, are necessary for the oxidation to happen, because if you have one of those CH bonds bound to the carbon bound to the oxygen, okay? If you have a hydrogen on the carbon bound to oxygen, then those hydrogen can serve as a beta proton, be removed by water. This beta elimination reaction. This is a E2 elimination. Is this E2 elimination? You can treat this guy as a leaving group. So this is a leaving group, okay? This is a leaving group, okay? This is a beta proton. That's E2 elimination. So if you have one of the, at least one hydrogen on the carbon connect to O, that's capable undergo, the beta elimination reaction, give you a corresponding carbonyl compound, okay? Now, if the aldehyde somehow, if you have water there, so this reaction, if you start from primary alcohol, you should have received aldehyde as the at least one step the product of the one step. But because if you have water in the system, the water will react with aldehyde, become this guy, and this guy, okay, it can react with chromic acid again because it has a two OH group. It reacts with the chromic acid. So this one's nucleophile, okay? It attacks here, okay? And it's go like this. Eventually, you're gonna have. We will not go through the every detail of the mechanism, but you will have this is a chromate ester again. So now you have the OH and H. Okay. So in this compound, okay, you still have a CH bond on the carbon bound to O. Okay. So if you make this guy, if you consider this whole thing, okay, is a living group. Okay. This is a living group. Okay. So then you have water to take the proton away, then undergo standard, you know, the E2 elimination. Yes.
Why do you have a double bond
Where double bond?
from oxygen on the bond?
It does have double bond.
But you showed as an error,
Huh?
as an error, you showed that it moves. Untapped,
But that's a few other steps, you know, because you know I'm not just limit of time. Okay, there's other steps because there will be protonation, you will be protonation on this carbonyl, then you know some further transformation because obviously you're gonna lose one oxygen, you're gonna lose water here. Okay, because you originally had 2 OH group, right? You only have one, so there's a few other steps, but it's good catch. Okay, but just you know, I'm not showing every step. Just you know, this is just you know this is a nucleophile attack this electrophilic chromium. Okay, then the you know you bond to this chromium, then this double bond will become single bond hydroxide ion. Then it will become alkoxide ion. Then receive a proton from acid, become hydroxy group. But there's a lot more steps. But we not at the position discussed in great detail. But we will get this chromic ester. Okay? This is pretty much works the same way as the Fischer acidification reaction. You know, if you see that we also should have learned that if you have Fischer acidification reaction, this actually works same way. You're gonna have the RO So that's a Fischer acidification reaction. What you see is the common feature is in both of those reactions, the alcohol serves as nucleophile. So in the formed product, the entire alkoxy group come from the alcohol part. So there's no change in the carbon-oxygen bond in the alcohol. No change in the carbon-oxygen bond on the alcohol. So the connection is always made the alcohol-oxygen bound to the electrophilic atom in the acid. So in case of a carboxylic acid, the electrophilic atom is a carbonyl carbon. In case of chromic acid, the electrophilic atom is a chromium atom. Okay, so the reaction is fully comparable. Okay, so then now to come back to this topic is basically what you see is the elimination. The key after key elimination step, you will have the carboxylic acid as an organic product, and the chromium component will become this. Okay? Obviously have acid here, acid hydronium ion. So that's why the aldehyde, okay, primary alcohol. If you oxidize, it using chromium 6 in water will become carboxylic acid. Okay. Now, if it's secondary alcohol, let's say using one secondary alcohol, do the same thing with chromium 6 acid, okay? What you will see is first step, the chromate ester will be this guy. That's the first chromate ester. And then this chromate ester will undergo E2 elimination. Give you the ketone product. And obviously you're gonna have hydronium ion, you're gonna add the reduced chromium species. And now what you can see the ketone, on the ketone, okay? Ketone carbonyl carbon, there's no more hydrogen there, okay? So ketone cannot be further oxidized, okay? No more hydrogen here, okay? No more hydrogen. Okay, so that's why secondary alcohol, you know, if you treat with chromium 6, it will give you ketone. Will never get into carboxylic acid. Okay. Now, tertiary alcohol, like here, you will not be able to oxidize by chromic acid, okay, or you call Jones reagent, because if you think about it, at the first step, you may form chromate ester, okay? But now you see the on this carbon, do you have any hydrogen there to undergo beta elimination reaction? On this carbon, there's no hydrogen, zero hydrogen, okay? Zero hydrogen, okay? Zero hydrogen. So there's no elimination possible, okay? So that's why I'm gonna show you here, you know, if it's a primary alcohol, you're gonna have a equilibrium reaction first, okay? And you treat with chromium 6 in, say, hydronium in water. You will get this guy. Then, you know, the beta elimination is possible. Well, happens really well. And give you the aldehyde and hydronium ion, okay? And aldehyde will further react with chromium 6 hydronium ion into carboxylic acid. Now, if it's a secondary alcohol, yes, it will be equilibrium. And you still can have water. Take this beta proton away. Become ketone. And reduce the chromium species. Plus hydronium ion. And the reaction will stop here because no further oxidation is possible, okay? Because there's no hydrogen available on this carbon to be oxidized, okay? Now, if you have a tertiary alcohol, the reaction only stop at this equilibrium because there's no hydrogen on this carbon to undergo elimination. So this reaction just stops at this equilibrium. And this equilibrium is actually mostly favor the left side. So tertiary alcohol is not oxidizable by the chromium 6 source. So these are if you treat alcohols with just say Jones reagent, what kind of product you will be getting, depending on what kind of alcohol you have. But what if I want to stop, okay, the reaction of primary alcohol? Basically, we know that tertiary alcohol won't react. Secondary alcohol will stop at the ketone. And primary alcohol, if you treat it with chromium 6 in aqueous environment, you get carboxylic acid. But what if I want this? The key part here is water, okay? So if you don't have water in the reaction system using non-aqueous, the chromium 6, you actually can get to stop the reaction at aldehyde. So if you want this thing to stop at the aldehyde stage, you will need PCC or PDC. They are basically the non-aqueous chromium 6. Both are, you don't know exactly what these two things are. Both of them are non-aqueous form of chromium 6. Non-aqueous, okay? And water-free. It's important. Water-free form of the chromium 6. They are oxidant and no water involved, okay? Because water is needed, okay, for the aldehyde to be further oxidized into carboxylic acid. So where did I show you? Yeah, yes. So the water is needed for the aldehyde to be further converted to diol, okay? So if you don't have any water in the oxidation system, you can actually stop the oxidation of primary alcohol in aldehyde. So you're gonna use chromium 6 source that doesn't have any water. The solvent also cannot be water, obviously. Most commonly using dichromethane as a solvent. That's a classic solvent for this reaction. So if you want to oxidize primary alcohol to aldehyde, you have to use PCC, PDC. PCC or PDC. Either one of them will be fine. Any other questions? Now, if no question, let's have a break for like 7 minutes or whatever. Then think about what kind of question you might have.